Alright, this video we're going to talk about section 3.2, day 1, the law of cosines. So in the previous lesson, beginning of 3.1, we saw that if we're given side, 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 or side, angle, side, we can solve a triangle using the law of cosine. So on the screen right now you see three standard forms of the law of cosines and then an alternative form that has been solved for the cosine of A. So if we're trying to solve for a side, we want to use the standard form. If we're trying to solve for an angle, we're going to try to use that alternative form. So just jumping right in, find the missing three angles of the triangle shown below. So we're trying to find angles, so we want to use that alternative form. Now it's not mandatory, but it's a really good idea to start with your biggest angle first. And this is going to take a little bit of the guesswork out of some things later. So looking at this, we have a side of 8, a side of 14, a side of 9. So that means cosine of B, or not sorry, cosine of B, but B is going to be our biggest angle. And we know that because it's across from the biggest side. So we're going to start with trying to find cosine of B. So using the alternative form, we know that cosine of B is equal to B squared plus C squared minus A squared over 2BC. So plugging in everything that we know from up here, we know that cosine of B is going to be equal to approximately negative 0.45089. Now this is going to be useful because we know cosine's negative. So if you think about your unit circle, cosine's negative in quadrants 2 and 3, but quadrant 3 is bigger than 180 degrees, so we're not even going to worry about that. So from this alone, since we know we're going to be in quadrant 2, we know that this is going to be an obtuse angle. Now why that's going to be useful is triangles can only have one obtuse angle. So we know that the other ones are going to be acute. We don't have to worry about two possible things working out for our sines or cosines of angles later. So all we have to do is use our arc cosine of that decimal right there. So arc cosine of negative 0.45089, and we're going to get approximately 116.8 degrees. So there's our obtuse angle. Now, if you wanted to, you could solve for cosine of A and cosine of C using our law of cosines, but law of sines is a little bit easier, and now we have a side and an angle. So we can come up with, let's go with A next. We can say that 19 over the sine of 116.8 is got to be equal to 8 over the sine of A. So we know that the sine of A is going to be equal to 8 sine of 116.8 over 19, which is going to be approximately 0.37583. So we can use our inverse sine of that decimal. And we're going to figure out that that is going to be 22.08 degrees. Now, on the law of sines problems, when we did this, we had to say, well, B, call that, I'm sorry, not B, but A, call that A. A could be 22.08, but A could also be 180 minus 22.08, and that could potentially give us two triangles. But since we already solved for our biggest angle, we know that this can't be an obtuse angle. So the 180 minus 22 isn't going to work, so it has to be just the 22.08. And since we have two of the three angles, we can say that angle C is going to be equal to 180 minus 116.8 minus 22.08. So C is going to be equal to 41.12 degrees. So law of cosines, sometimes it's easiest if you just use it once and then go back to your law of sines to get the rest of them. You could continue doing your law of cosines over and over again to get these other two angles here, but law of sines is a little bit quicker, a little bit easier. Alright, so looking at the next example. So we had side, side, side before, now we're looking at a side angle side. So find the missing pieces of the triangle shown below. So if we look at it, we need a side and we need two angles. Angles are easy to come by if we have law of sines. But nothing really pairs up, right? We don't have an angle here and this here. We don't have an angle here with this here. We have this angle and this side that we can find. So we can find this. That's going to open up a pairing that's going to allow us to use law of sines instead of law of cosines. So if we think about what the law of cosines says, it says a squared equals b squared plus c squared minus 2bc cosine a. And you don't have to have these memorized. I'll give these to you on any sort of assessment. So we know that a squared is going to be equal to that, so we can just plug in what we know about BC and cosine of A. So if you plug in 15, 10, and 115 degrees, a squared is going to be approximately equal to 451.79. And then if we take the square root, a is going to be 21.26. And now we have this pairing A and angle A. So to find angles B and C, we can just set up our law of sines. So let's find B next. We'd say 15 over sine of B. And then if we wanted to set up for C, we can say 21.26 over sine of 115 equals 10 over sine of C. And I'll leave that to you guys. Pretty straightforward. We've done it a few times. Finding B and C from there. And there's one more real quick example, and then we'll call it quits on this video. Pitcher's mound of a women's softball field is 43 feet from home plate. The distance between the bases is 60 feet, as shown in the figure. How far is the mound from first base? So one thing to note is the pitcher's mound is not halfway in between these two things. So this right here is not going to give me a right angle. This is not a 45, 45, 90 right triangle. If the pitcher's mound was exactly halfway through, we would have a 45, 45, 90, but we don't. This is not halfway through, or halfway between the two. So what we're trying to find is just H, which is a side, and we know its angle that's across from it. So this is a side angle side one. So we can say H squared is going to be equal to P squared plus F squared minus 2 times FP, or 2 times F times P times the cosine of, we'll call it cosine of H, but really we just mean this angle here. So, plugging everything that we know in, we're going to get that H squared is approximately 1800.3, which makes H, the distance between the pitcher's mound and first base, approximately 42.43 feet. So that's going to do it in this video. We will see you in the next one.